Hello everyone, my name is Behshad Aliyari, and today I am here to present my Java-based application that I made to translate MIPS machine code, MIPS to machine code. Um, this was our project for CS222 and CS224, and I have taken inspiration from our professor's provided code. This is just the shape of our code, basically how the text fields and the borders look like. And for example, this is one of the given examples by our professor. So in the end, what we want is a page like this, a border like this. On this side, we enter MIPS assembly code and we click on a convert button. And over here, we would have translated the given code into machine code and address. So for example, here we have again add $T0, $S3, and $V0. The code is translated into machine code, and this is the hexadecimal of our code. We also have the address of our uh, registers, which is also shown here. So I'm going to briefly explain what I've done with my code, and then I will run some examples. So I basically made a, let's say, the goal of this application is to basically simplify the process of converting MIPS assembly instructions into machine code. And it's really helpful for students or learners who want to visualize how different types of MIPS instructions are encoded in hexadecimal format. And my application, which I have created, with just one single click, we are translating each instruction of MIPS, and we're going to display it in the corresponding machine code along with its memory address. And over here, this is going to be my GUI Java code. This application was created using Swing GUI, which I have imported using import Java. This is one of the utilities of our Java programming language. Um, uh, Basically, on the right, I want to explain on this part a little bit. So basically, users who are using this code basically can see the machine code and the address on the left side of the page, and uh, on the right side, I'm sorry, on the right side, they can see the address and machine code, and on the left side, they can enter their own code. Um, Basically, the memory address in this program starts from 0x00400000. So it's 004 and 6 zeros, as you can see right here. This is where our program starts from. There's also a convert button over here, which processes the input. And I also created a, let me run my code for you to see. This is my version of the translator. So I have over here my input file. So I will input any type of MIPS assembly code that I want to see the output of. And over here, I would have the address for the code and also the machine code. Over here, I have the translate button, which basically is the same thing as the convert button here, but I just changed the name. And I also added a bonus um, program right here, which clears the everything that we have wrote here and everything that we have here. It's a little bonus that I added here just for, the beauty of the work. So, so far, I've basically explained what we did. And I'm going to talk about the supported instructions that are inside of this Java code. So we have R types and L types and J types. So for the R types, we have add, as you can see here, we have add, we have sub, and, or, SLL, which means shift left arithmetic, and SRL, SLLV, SRLV, and etc. We also have the L types like ADDI, like this one, ANDI, LW, SW, big equal, which is BEQ, BNE, and BLEZ, BGTZ, which we will not really use those, but those are our L types. We also have J types like J or JAL. Um, this program right here, it handles labels and computes the correct offsets for branch and jump instructions. Uh, they're kind of tricky in manual encoding. So my code is built in a modular way. Let me explain the key components. So the input and output areas are text areas that are created using JText area. As you can see here, we have used JText area. So as you can see, these are the simple stuff. This is like the name of the app. Um, this is the title, as you can see, the title of our code. This is the size. For example, it's 1000 pixels to 1000 to 550 pixels. We also have this exit on close, which when I press this, it will exit. Um, I mean, it closes the code. This is the input area, which we have explained here, and the output area is going to be here. We also added the JSplit pane so that we split this whole interface into two pieces. And I've created panels. This is our first panel, which is the input assembly, which we will put our input inside. This is the output area, which is called machine code output. And I've resized the borders that I've created for each of these panels. We also have the translate button and the clear button. This is basically the action listener. So when I press the translate button, it will do this. Or when I press the clear button, it will do that. That's basically what I've done here. This is just the, so for example, there is nothing written here, so it's just empty. I given both of them an empty space so that we can start writing code. We also have a control panel for both of these translate button and clear buttons. Um, I've added the split pane. These are the components for the frame, basically, nothing too crazy. So for example, this is in the center. You can, of course, change the size of this, but on default is in the center. So we are initializing the text area with the editable flag. So for example, jtext area equals new text area, and I have chosen the monospaced code, monospaced font, which as you can see is very similar to how, if I could show you, sorry, if I could just show you, if you, if you pay close attention, uh, this is the same type of, I don't know if I can show it to you, but this is the same font that is used in Mars 45 MIPS assembly. Just a little bonus right there. I tried to make it as close as possible. So yeah, I used that font. Uh, the size is 14, nothing really important right there. This is just editable, nothing crazy. This is the panel with the title and the scroll panel that we have our text area. So the border factory, border layout is in the center, the scroll panel. These are just graphical codes, nothing interesting yet. And then I have processed the translation. So this is basically the important stuff is happening inside of this code right here or here. process translation. So this is basically what happens every time we press on our translate button. So what it will do is it's going to split input into lines so that it's not going to launch and translate every bit of a code at once. It's going to split them into multiple lines and translate them each by each. So this is the output, this is for the clear output area, which is this button right here. Um, we have identify all labels and their corresponding addresses. So we have created an integer called current address, and it will start at address. So this is the start error for our translation, and if you remember, it was 0, 0, 0, 4 and 5 zeros. That's our starting address. Um, we also start from that. This is the white space for our line. As you can see, this is the white space for our line. Uh, if our line is empty, this is just skip empty or label lines. This is something extra. So we are trying to encode the instruction into machine code and append it to the output area. So we have a string called machine code that will encode instruction trimmed line current address, and it's going to append our given input into the output area, which will use the format of this format that will handle, uh, as you can see, it will put the current address in the machine code right here. This is the format that we used for our string. Also, there's a catch for inspection. When we have an error, it will just write error, and this is the error handler. Basically, it will print error at the end of our code. And this is going to increase the address. So it's going to increment the address by 4 because every instruction in MIPS assembly is 4 bytes. We also have identify and store labels to their addresses. So identify labels starts from in we have the int address, which starts address. For string line equals lines, we have trim white space again, and we are going to have label address map, which is going to store our label address. It's going to put it in a target and a replacement. Uh, Otherwise, if it's empty, it's just going to increment the address for non-label lines. This is for encoding the instruction into machine code based on its operation. So what I have done right here is that I have given every possible operation that the question wants us. So these, for example, are R-type operations. These are the L types. These are the I types, and these are the J types. So what I've done here is that I've explained all of those into here and what the function does. So for example, as you can see, add starts from 0x20, which is the hexadecimal function for it. And these are the tokens. So this is for like the R types, L types, and J types. This is the jump, this is the branch, L type, load, store, shift, all of the operations and their corresponding version inside of Java. Default is not supported because it will return if operation is unsupported. So if you, example, put something that doesn't exist, it will just return it, and because it's not supported. So over here we have encode R type instruction. So what it is doing, for example, for add or subtract, is going to register our code for the instruction that it is. So for here, I have RS, which is the register RS. It's going to integer equals get register code RS. Or for RT and RD, we have all of those here. This is going to return them into a format of hexadecimal, and it's going to make sure that it's less than 21 and less than 16. So for RS, it's going to be less than 21. For RT, it's going to be less than 16. For RD, it's going to be less than 11. It's going to format them, and it's going to return us the hexadecimal equivalent. So we are here for the shift instructions such as SLL or SRL, and this is going to give us, for example, this is for encode shift like string RD, RT, or sham. It's the same thing like the up here, but we're doing it for SLL and SRL. This is for the I-type instructions such as ADDI or LW. We have the opcode, the RS, RT, and IMM, and it's going to return us the hexadecimal version in return. We also have the load store instructions, for example, the LW and SW. Right here we have our integer and our string. So our integer is called offset. It's going to give us and extract us the offset of the instruction. The string base is going to extract the base register. And it's going to give us it as a return for our I types. And this is going to return all of the details or information that we have as an I type. This is for the branch instructions such as BEQ or BNE. And basically we have offset again over here, but it's going to calculate the branch offset. And it's going to encode it as I type. Same thing here, but for branch offset based on the label. So if our string is labeled and integer PC, it's going to give us the label address map, and it's going to calculate the offset. This is how you calculate the offset, by the way. We also have the jump instructions such as J or JIL. Um, it will do the same, but it's going to jump from the target address, such as the start address that we have added. This is 00450. And this is the target address. It has to be equal or bigger than this. Return the formatted machine code. This will return our opcode for the J types. We also have all of the register names and we have to map them. So for example, $0 means 0 or $@ means 1, $V0 equals 2. So basically we're just mapping all of these instructions that are only available in MIPS assembly to a meaning or a translating in Java. So if the program sees this, it's going to do this. That's basically what it's doing. And at the end, default is going to give us 0 if it's an invalid register name because it doesn't exist. And over here, we have the format the value to hexadecimal string. So everything that we got from the code is going to be turned into hexadecimal. And as you can see, it's going to format the string into hex, which is here. And this is the main method to launch the application, which I just put all the way down here. This is just the main method. So swing utilities, invoke later. This is just to launch the GUI, nothing interesting. This is what has to be in the front, but it's on the back. I've explained everything about the code by now, and I'm going to solve a few examples. The first example that I'm going to do right here is the same thing that our professor provided. And this is the code that our professor gave us. And I'm going to show you the conversion. So if I tap on our translate, it's going to give us all of this machine code. So basically, what's going on here is we have again and we have x1. So we are adding $T0. We are adding $S3 to $V0 and storing it in $T0. This will be stored in 0040000. Over here, we're adding to $0, we added 4, so it will look like this. This is the address, this is the machine code. Basically, for each line, we are going to have the equivalent address and the equivalent machine code right here. So as you can see, this is a negative number. So negative numbers are shown using F in hexadecimal. So we have F right here. Uh, just the same thing here. I just want to show you that this is the same result as the given code right here. This is the same result right here. But of course, I have some extras, like I can write it right now. We could say, let's say add dollar sign, sorry, dollar sign, let's add dollar sign T0 uh, plus, no, let's add dollar sign S3 to dollar sign V0, dollar sign V0. This is basically what we're doing is dollar sign S3 is going to be added to dollar sign V0 and it will be stored in dollar sign T0. Basically, that's the whole thing that's happening right here. So if I translate this, we're going to see this. So this is the address, which is the default, and we have uh our, I'm sorry, let me edit this real quick, and let me take this, delete that, let me clear this, translate. This looks a bit better in my opinion. Yeah, this looks way better. And or I have some. Oh wait, I have some here. Let's just use these and put them here. Let me just clear this. Put this here. And this is we are over here. What we have is subtracting dollar sign T0 by dollar sign S1, which will give us this output. We have many more. I could do many more. We could do one with BEQ, dollar sign, and do dollar sign S3 with dollar sign S2. Sorry, that's not dollar sign. Dollar sign S2, and let me see. We could go with a loop one. Let's go loop, and it's going to give us FFF at the end. There's multiple things that we can do right here. These were just some examples. I can do more. For example, I can just write uh I can just write J. So it will give me the machine code, I mean the address, but it will not give me the machine code because it's an error. I could have and dollar sign T2 and dollar sign V1, dollar sign A2. If I translate this, we're gonna have this number. This is our machine code. This is our uh, address for our registers. There's multiple things I can do right here. I can go SLL, dollar sign S2, dollar sign T1, and 2. Translate this, we have this right here. There's many more I can do here, but these were some simple uh, these were just some simple examples that I have done right here. So yeah, that's basically much everything that I have done here, and I hope that you enjoyed this video, and that's it. I see you later and have a good day. Bye bye.